I think we can start the lectures to the hour. Yeah, so in today's lecture, today and tomorrow's lecture, we will actually learn how to analyze AC circuits. But in today's lecture, we will look at a circuit which still doesn't have an alternating voltage source or an AC current source. So we'll just look at an inductor and a resistor and an inductor and a capacitor together in a circuit, as well as three of them in the circuit. So just a quick review. Yesterday we learned what an inductor is. It's a circuit device that sort of acts like the resistor counterpart in AC. It essentially makes it difficult for rapid changes for current to occur, because we learned from Faraday's law in electromagnetic induction that if the current changes, then you have a changing magnetic field that induces a voltage or EMF, and that induced voltage is to oppose the change in the current or magnetic field. So we learned that yesterday, that's the main purpose of the inductor. And also the inductor stores energy, and energy stored in its magnetic field. This is the amount of energy stored. It depends on the current in the circuit and the inductance of the inductor. We also learned yesterday, that the inductor, if you have a changing current, as I mentioned earlier, which generates a changing magnetic field, that then creates a induced voltage across the inductor, and the voltage across is given by this equation, which was the definition we used to define what the inductance of the inductor is. So now let's look at what happens if we put an inductor in a circuit. I connect that to a battery, a voltage source. You have a resistor. This resistance could either be an external resistor that you add to your circuit, or it can be the internal resistance of the inductor or the wires in your circuit, right? So we learned before that the convention we're using is that the current will flow from, once you close the switch, the current will flow from the positive terminal or high potential point of the battery to the low potential point of the battery. But we also saw that an inductor will oppose any sudden change in current in the circuit. So because you have an inductor in this circuit, then the current cannot change automatically or suddenly from zero when the circuit is open to some current value when you close the switch. So to see how the current behaves once the switch is closed, let's analyze the circuit. They're all connected in series, the battery, the resistor, and the inductor. According to Kirchhoff's loop rule, the voltages add up when circuit elements are connected in series. You have, if you go around the loop in this direction, then you have a voltage rise across your battery, you have a voltage drop across the resistor, and a voltage drop across the inductor. And the sum of all the voltages should equal zero. Now, what we want to find is the behavior of the current. So current occurs in two of the terms here, and you have a derivative in current in the third term. So if we work out the maths, and I will let you follow through with the maths yourself, but essentially the key idea is to collect all terms containing currents on one side and terms containing time on the other side. So you have dI together with currents on one side and dt on the other side, so that you are able to integrate the equations. And by doing the integral, you will find that the current in the circuit will be described according to this equation, right? You have an exponential equation, and of course, it depends on the maximum current that the battery will provide to your circuit. Okay. In this term here, we defined a variable tau, which we call the time constant, defined as the inductance over the resistance. We'll talk more about the significance of this time constant tau, but first let's look at this equation, right? If we make a graph of this equation, it's essentially an exponential, but you have 1 minus an exponential. Essentially, you have this exponential increase in the current following this equation here. And as time progresses, the current in your circuit increases according to the energy that's being stored in your inductor, right? And just a reminder, the energy that's stored in the magnetic field of the inductor depends on the current in your circuit, so that if your current is maximum, then you would have stored the maximum energy in your inductor. Okay. Right, so your current increases up to a maximum value. The maximum value will happen after a very long time. So when you put this equation, time approaching infinity, then e to the exponent of negative infinity is essentially 0. So your maximum current will be equal to the battery voltage over the resistance. In essence, it's the maximum current that your battery will produce in the circuit. That will be the maximum current that you have. Then we define this time constant, which is L over R, inductance over the resistance. It's defined, it's defined as the time it takes for the current to reach 0.63 or 63% of the maximum value. And this is nothing new, because we encountered this with a capacitor, right? When we talked about a capacitor charging up, right, we also encountered this time constant, and this 0.63 or 63%, that came from setting time t is equal to tau and working out this equation. You'll see that you'll have 1 minus 0.37, which is 0.63. Okay, so that's the time constant. But physically speaking, the relevance of the time constant for an LC circuit, LR circuit, is that it defines how fast energy is stored in the inductor. So sort of, if you draw parallels with the capacitor and the inductor, they're sort of doing similar things. They store energy, except that for an inductor, the energy is stored in the magnetic field, because you need this change in the current in order to store the energy in the magnetic field. Whereas for a capacitor, the energy is stored in the electric field between the plates of the capacitor. Right? Cool. Now, once your inductor is fully charged, right? So initially you have this circuit with a voltage source or a battery that charges up your inductor. Once your inductor is fully charged and you flip the switch to position B, such that you isolate the inductor and the resistor from the voltage source, in essence, you only have this circuit containing an inductor and a resistor, right? Because you have an inductor here, the current will not automatically go to 0 right away, even if you disconnected the switch from the battery, right? As we've been discussing, the inductor will create an induced voltage and an induced current that will oppose any change in the current in the circuit. So it won't automatically go to 0 instantaneously. So again, let's see what happens to the current, or how the current behaves once we disconnect this LR circuit from the battery. If we do again Kirchhoff's voltage rule and we add up the voltages in this circuit loop, you only have a resistor and the inductor. That means their voltages should add up to 0. Okay. And you have these two terms, they both contain currents. One is a derivative of current with respect to time. If we do the maths once again, so that on one side we collect terms containing currents, you have there the derivative of currents over the current, and then you have there the derivative of time. If we integrate both sides, we get this equation that describes the current in the circuits as you disconnect. If you have a fully charged inductor that's disconnected from the voltage source. So you see, again, this exponential function, which tells us that if time t is equal to 0 at the initial time, when you disconnect the inductor from the battery, you start from a maximum current, the maximum current that's coming from the stored energy in your inductor. But then as time progresses, as time approaches infinity, the current decreases and it approaches 0. So it's described by this exponential decrease here. If we set time equals the time constant tau, we again get this 0.37 times Imax. Yeah. If we set t equals tau here in this exponential function, we again have this time constant tau, which is the time it takes for the current to decrease to 37% of the maximum volume. And if, right, so if we analyze this graph, then since the current decreases to 0, it means that the energy stored in the inductor decreases, until there's no energy left. Of course, the resistor dissipates the energy that's coming from your inductor. You again have this time constant, but physically it defines how fast the energy is released from the inductor. So it's again, if you draw parallelisms with the capacitor, it's again has the similar concept with the discharging of the capacitor, right? Where the charge stored in the capacitor decreases exponentially until it reaches 0, and the time constant tells you how quickly the capacitor discharges. For the inductor, the time constant is the dissipation of energy stored in the inductor, which is related to the decrease in the current in the circuit. Good, right? So hopefully nothing so much new there. But what we can see here is that because there is an exponential increase and decrease in the current, there is some reaction time whenever you have a device that has an inductor. And that's why inductors can act as surge protectors for sensitive electronic equipment, because it prevents the sudden increase and decrease or sudden surge in the currents in the circuit. Yeah. And it does that, of course, by inducing a voltage in the inductor. Okay, so just this slide summarizes all the relevant equations for the energizing and de-energizing of the capacitor that we have seen. So maybe it will be useful when you're sitting the tech test. But let's look at this example of an LR circuit. You have a 12-volt battery. It's connected in series to an inductor with this inductance, 220 millihenry. That circuit has a total resistance of 30 ohms. Okay, and we take time t equals 0 as the time when you close the switch and when current, when you close the switch essentially, and current starts to flow after that momentary period. Okay, so current at time t0 is just when you close the switch, right? Just at the moment when the switch is closed. So as we have been learning, the current should increase gradually, exponentially, according to the exponential equation we derived. So at the moment when you close the switch, the current should still be 0, because the inductor will prevent the sudden increase in the current. Momentarily, the current will still be 0, and then it gradually increases well, exponentially increases to some maximum value. Okay, the time constant, it's from definition. It's the ratio of the inductance. Okay, and don't forget to expand that prefix milli. That's inductance L, and then divided by the resistance R. Right, so at this time, the current would have reached 63% of its maximum value. And that's the maximum current. The maximum current is provided by the battery, okay, assuming that you only have the resistor there. Okay, so the voltage is given and the resistance is given. So this will be the maximum current in your circuit, which will also be the current when your inductor becomes fully charged. Okay. Good. Okay, here's some example of the mathematical manipulation of the equation. We want to know how long it will take. Essentially, we're looking for the time it takes for the current to reach 1/2 of its maximum value. The equation for the current is, of course, given as derived previously. This battery voltage over resistance, that's the maximum current that your circuit can have, and we calculated that earlier. So essentially, we're wanting to find time. So we want the time when the current is equal to 1/2 of the maximum value. We're just replacing this currents with the required currents. Okay, current is 1/2 the maximum value, which essentially you can cancel out maximum current in both sides of the equation, or you can think of it as we need this bracketed term to be equal to 1/2. Right, and we want to find the time. Time is what we are after, so it's a matter of rearranging this equation. You have this exponential function tied up with this 1. So you isolate your exponential function by rearranging this, right? You're isolating your exponential function by itself. You have 1 minus 1/2, right? And then that's essentially, this is just 1/2, right? It's easy. That's just 1/2. And to get rid of the exponential here, right, in order to isolate time, you do the reverse of this power base E. That inverse is the natural logarithm. All right, so if you take the natural logarithm, or ln, of both sides, the ln cancels out the exponential, and you're just left with minus t over tau on the right hand side, whereas on the left hand side you're getting the ln of 1/2. Good, right? Okay, and then it's just a matter of algebraic manipulation. So time there, you have to multiply with negative tau in order to isolate time. Tau, of course, the time constant was calculated earlier, or you can always get it L over R. Okay, this was the earlier calculated time constant, and this is the ln of 1/2. Okay, so you get this time. Good. Any questions there? Right, and the last question, rate at which the energy is being delivered by the battery at the instant when the current is 1/2 the maximum current. In other words, when the current is equal to 1/2 times the maximum current we've calculated, or when the current is 0.2 amperes, Okay, how quickly is the energy being stored in the inductor? Okay, rate of energy, that means when you say rate, that's energy divided by time, right? What is energy divided by time? It is power, right? Power, the definition of power is how quickly energy is being used up, or in this case, it's how quickly energy is being delivered by the battery to the inductor. So in other words, we want to find the power. We know the current. The current is given as 1/2 the maximum current, which you find here, and the voltage of the battery is given. So you have 2.4 joules of energy is being delivered per second, or 2.4 watts of power is being delivered. Good. Right. Any questions about the example or the concept of energy storage in the inductor, or energizing and de-energizing the inductor? So I hope it sounds a bit familiar, because it's, you know, it's just like the capacitor charging and discharging. Now say you have an inductor and you connect that to a capacitor, that gives you an LC circuit, LC inductor capacitor circuit. The underlying idea here is that the capacitor is fully charged, so that you have initially a source of energy. Okay, energy. Essentially, the capacitor is fully charged means maximum energy stored at the capacitor, between the capacitor plates, and then you connect that to an inductor. Of course, the circuit is a closed circuit one, and so current is able to flow. Just like the discharging of a capacitor, the capacitor sort of acts like the voltage source. You have a positively charged plate and a negatively charged plate. The current will then flow from the high potential point to the low potential point. Okay, we can, again, if you want to see what's happening to the currents in the circuits, we again do the same strategy we did. Using Kirchhoff's voltage rule, we add up the voltages. Here, going through the loop like this, you have a voltage rise across the capacitor. So that's the voltage across the capacitor, and a voltage drop across the inductor. Recall that current, the definition of current is how quickly charges flow, right? When we learned about current, it's the rate of flow of charges. So current is essentially dq over dt. It's related to the charge in your capacitor plates. And the negative sign here tells us that the charge in the capacitor plates decreases as your capacitor discharges through the inductor. Okay. So you then have this equation, right? It's a differential equation, second order differential equation, because you have this second derivative with respect to time of the charge, plus you have this another term, which is a function of charge. And if you have a second order differential equation, the solution to that is a cosine function. So if we solve the second order differential equation for the charge will be equal to maximum charge times cosine omega t. This is, from definition, the solution to a differential equation. Okay. Right, so let's look at this equation. That's the amount of charge, that's the rate at which charge is being dissipated from your capacitor. If we look at the current, of course, current is dq over dt, or rate of change in charge. So if you take the derivative of this charge equation, you're essentially taking the derivative of cosine omega t, right? Derivative of cosine omega t is, derivative of cosine function is negative sine omega t times the derivative of the factor here. Derivative of omega t is omega, right? Hence, you have the current equation as omega q max sine omega t. Right? We're just looking at the absolute values because we know the current there will decrease through time, where omega is the angular frequency defined as 1 over square root of LC. Right? So you have charge being defined by a cosine function and current defined by a sine function. If we plot these two functions in a graph so that the charge is a cosine function with respect to time. So you have here the y-axis is charge, x-axis is time. When time is equal to 0, cosine 0 is equal to 1, hence you have maximum charge. Whereas for the current, it's a sine function. And at time t equals 0, sine 0 is equal to 1. Hence you have, sorry, sine 0 is equal to 0. Hence at time t equals 0, the current is 0. So what you can see here is that if the charge is maximum, the charge in the capacitor plates is maximum, then the current in the inductor, right? We're talking about charge in the capacitor and current in the inductor. Here, they are inverse of each other, right? If charge is maximum in the capacitor, the current through the inductor is 0. If the charge in the capacitor is 0, that means it's fully discharged, then the current through your inductor is maximum. And the frequency for which this interchanging of charge and current occurs is given by this frequency. It depends on the inductance and the capacitance. We can therefore still expand the definition of frequency, recalling that frequency, angular frequency is 2 pi f, right? Angular frequency omega is 2 pi times the normal frequency f. Hence, we have frequency, normal frequency being related to the inductor and the inductance and capacitance. And just a further definition, period is the inverse of frequency. So just some definitions here relating different quantities: angular frequency, normal frequency, and period. But the key takeaway I want to say is that you have this oscillating relationship between the charge that's stored in the capacitor plates and the current that is through the inductor, right? And if we relate that to the fact that the capacitor stores energy in the electric field between its plates, and the inductor also stores energy, right, in the magnetic fields between its coils, then therefore we can see that since if the charge is maximum in the capacitor and the current is minimum in the inductor, we can then also say that in terms of the energy, if the energy stored in the capacitor is maximum, then the energy stored in the inductor is 0, right? And then as the capacitor loses charge, capacitor gets discharged, it loses energy that's being stored in its plates. Where does the energy go? It goes to the inductor, right? As the current in the inductor increases, the energy stored in the inductor also increases until you have this maximum maximum energy being stored in your inductor corresponds to minimum or zero energy stored in the capacitor plates. And if you follow this graph, you will see that there is oscillation between the energy stored in the capacitor and the energy stored in the inductor. Okay, at time t equals, at this particular times, 0, 1/2, and time equals the period, you can see maximum energy being stored in your capacitor plates. At those times, your inductor doesn't have energy. Okay? But at time equals 1/4 times the period, 3/4 the period, you have maximum energy stored in your inductor, and those corresponds to the time when energy is 0 in your capacitor. Does that sort of conceptually make sense? Because both the inductor and capacitor store energy, right? And energy needs to be conserved. So we can see here that if the energy is maximum in the capacitor, right, stored in the electric fields, and then the energy stored in the magnetic field should be 0. So B here stands for magnetic field. And you have this interchanging or oscillating energy storage between your capacitor and the inductor. Okay. In terms of the equations, if we want to solve to quantify how much energy is stored, we recall that for a capacitor, the energy stored is 1/2 CV squared. C is the capacitance of the capacitor, V is the voltage across its plates. If we use the definition for the charge stored in the capacitor, we can rewrite this energy stored in terms of the charge that's contained in the capacitor plates. And so you have this energy in the capacitor, right? And then for the inductor, right, you have 1/2 Li squared for the inductor, as we defined in the earlier slides. Okay. Right, so the energy oscillates back and forth between the capacitor and the inductor, but still remember, energy is always conserved. So if we add up these two energies, the total energy in your system should be the sum of the energy in your capacitor plus the energy in your inductor. Of course, when one is maximum, the other should be 0. And if one is 0, the other is maximum to conserve energy. But in any other times when one or the other is not maximum, then you use this equation to determine how energy is shared between your capacitor and inductor. And recalling that the charge stored in your capacitor can be calculated from this cosine function, and the current stored in your current passing through your inductor can be calculated using this sine function. Good. All right. Okay, so are we happy with the concept of the LC circuit? It's essentially energy being shared, like, by the inductor and the capacitor there. Now let's look at an example. You have a 1200 picofarad. Pico is 10 to the minus 12. Picofarad capacitor. It's initially charged to this value, so we can take this as the maximum charge that is stored across the capacitor plates. It's connected to a 75 millihenry inductor. milli 10 to the minus 3 at the initial time t equals 0. And we want to find these things. All right, so for the maximum current, so for the current, we solve that the current in an LC circuit is described by a sine function, okay, where omega is defined by the inductance and the capacitance in the circuit. When we want the maximum current, right, the sine function just oscillates between -1 and 1, right? It's a sort of a circular function that oscillates between -1 and 1. So at maximum current, sine omega t will be equal to 1. So essentially, we are just wanting to find the current is equal to omega times the maximum charge, right? The maximum charge is how much the capacitor stores maximally, which is what's given initially. And omega, angular frequency, you can solve it from the definition square root of 1 over LC. So then the maximum current is the maximum charge that's given here, divided by square root of the inductance in Henry times the capacitance in farads. So don't forget to expand again your milli and your picos when you do the calculation. Right, next, what's the frequency and period of the electromagnetic oscillations? Meaning, what's the frequency for which the energy is transferred from the capacitor to the inductor, or how many times in one, when we say frequency, how many times in 1 second will the energy be in the capacitor, and in another second, the energy is in the inductor, right? That's essentially what this frequency of oscillations mean. But the frequency of oscillations is defined right, from omega is equal to 2 pi f, right? So f, rearranging that, f will be omega over 2 pi, where omega, the angular frequency, is described by the definition from the inductance and capacitance. So 17 kilohertz or 17,000 hertz means 17,000 oscillations per second. So in 1 second, 17,000 times in 1 second, the energy transfers between the capacitor and the inductor. And the period is from the definition of period being the inverse of the frequency, right? So 6 times 10 to the negative 5 seconds. After, for example, after 6 times 10 to the negative 5 seconds, the energy is transferred to the inductor. And then after another 6 times 10 to the negative 5 seconds, the energy is in the capacitor, and so on. Good. All right, the total energy oscillating in the system, right? Total energy can either be, can be solved 2 ways. If you think about the total energy being contained in the capacitor, then you use this equation, which relates to the energy stored in the capacitor with maximum charge. Okay. The charge is given here and the capacitance is given, so you are able to calculate for the maximum energy stored in the capacitor, right? Or we have been learning that either all of the energy is stored in the capacitor, or all of the energy is stored in the inductor. So therefore, you can also calculate the total energy in the system by taking the total energy that can be stored in the inductor, in which case you use the maximum current. right? And in that case, all the energy is stored in the magnetic fields. The inductance is given in the problem, and the maximum current was solved in the first question. Hence, you get the total energy. But what you can see is that you should get the same total energy because energy is conserved. It's either all in the inductor or all in the capacitor, or it's shared between the two devices. Good. Right. Cool. Are we happy with the LR circuit and the LC circuit? Okay. So LR circuit, you have the resistor, so it's either charging up if you have a battery, or energizing the inductor if you have a battery, or de-energizing the inductor if you don't have a battery. For the LC circuit, we assume there's no resistance and energy is conserved. And so energy is just transferred between the capacitor and the inductor. Now, what will happen if we combine all three? We now have, the LC circuit, but then you also have a resistor, because in reality, you have some resistance in the wires, and therefore in your circuit. Here we again start with a capacitor that's initially charged, because otherwise, if we start with a discharged capacitor, there's really nothing that's going to happen. But now we have a fully charged capacitor. What's the effect of the resistor? Okay, logically, when we think of the resistor, it's just like friction, right? It's like friction in your circuit. And so the resistor should dissipate the energy in the form of thermal energy. And that's why your wires heat up, or the resistor itself heats up. So in this case, you still have energy, being transferred from the capacitor to the inductor, but some of the energy is being dissipated by your resistor here. If we analyze what happens to the current in the charge, right, we again start with Kirchhoff's voltage rule. Okay, you have this positive plate. So if you do your Kirchhoff's voltage rule in this direction here, say in that direction of the current, so voltage rise across your capacitor, positive voltage across your capacitor, negative voltage across your inductor, and negative voltage across your resistor. So you have this Kirchhoff's voltage rule adding up. All voltages should equal to 0. And we again write up the current. Again, we use current is related to the rate of change in charge. So we can rewrite current in terms of charge, but this becomes a second derivative because you're taking the derivative of the derivative of a charge. And this I times R becomes the first derivative of charge with respect to time. But what we can see, every term contains a charge term. Okay. Right, if we solve this, it will be, again, a second order differential equation. It will be cosine and sine functions. We will not go into the details of that. But for this course, we will just look at the solution and interpret the solution here. So this is a second order differential equation for the charge. So if you solve this equation, you will have an equation that relates to the charge, how the charge changes with time. And the solution to that equation is given by this equation here, which is an exponential function with respect to time, but it also has a cosine term. We will only, for this course, as I mentioned, we will not go into a lot of details, but we will only interpret the important factors that we can derive from this equation here. And what this equation tells us is that because you have, so y-axis is charge, X-axis is time. If you look at your equation here, time is in the exponential term. And in your exponential term, you have their function of the resistance, R, and the function of the inductance, L. What that tells us is that depending on the relationship between the resistance and the inductance, there are three possible things that can happen in your circuit. Of course, we know you have an inductor and a capacitor, so there's still oscillation, right? There's still a transfer of energy between your inductor and your capacitor. But depending on how much resistance in your circuits, right, the oscillation can either be classified as underdamped. For an underdamped oscillation, this is when the resistance squared is less than, it's defined by this relationship here. In an underdamped situation, you will have some oscillation. So you will still have some transfer of energy from the capacitor to the inductor that is that is defined by this graph. So at some point, all the energies in the capacitor, at another point, some energy, not all, because some would have been dissipated by the resistor, but some energy would have transferred to the inductor, and then some energy, a smaller amount, as over time energy gets dissipated, a smaller amount is transferred back to the capacitor, and so on. That's for the underdamped case. Okay. For the overdamped case, this is when the resistor is very large, right? The resistor is greater than 4L over C. This is this orange graph here. Since the resistor is very large, in the process where the energy is being transferred from your capacitor to the inductor, a lot of energy has been dissipated already, such that almost no energy is transferred to your inductor. So yes, you can see there's almost no oscillation in the overdamped case. Okay. And for the critically damped case, where the resistance is R squared is equal to the inductance 4L over C, we call this the critically damped case. So you have a slower dissipation in charge, but still there's no oscillation. So maybe some energies reaches the inductor, but not enough to be stored in the inductor. Right. The frequency of oscillation we can see for this underdamped case is defined by this equation here. Okay, and I think for this course, up to the level of understanding what's happening to the energy between the capacitor and inductor in the presence of the resistor is sufficient. So are we happy with the concept there, like the effect of the resistor dissipating the energy? And just a quick example, you have here a 40 millihenry inductor. It's placed in series with a 3 ohm resistor and a 4.8 microfarad capacitor. We want to describe the behavior of the circuit, whether it's underdamped, overdamped, or critically damped. And then as a follow-up, how should we modify the circuit in order, modify the resistance in the circuit in order to have no oscillations between the inductor and the capacitor, right? No energy transfer between the two, in essence. Right, so to determine whether it's underdamped, overdamped, or critically damped, you have to look at these conditions for each of the damping. Right, so you have to calculate the resistance and compare that to 4L over C. Well, you don't have to calculate the resistance because it's given, but you have to calculate 4L over C. Right? So 4L, 4 times 40 times 10 to the minus 3 divided by 4.8 times 10 to the minus 6 gives you this 4L over C equals 3.3 times 10 to the 4. All you have to do is to compare this 4L over C to the R squared value. Okay, R squared is less than 4L over C, and that satisfies the underdamped motion. So there is some oscillation that will happen, and that will decrease in amplitude over time as energy is being dissipated by the resistor. Now, so how do you modify the resistance so that there is no oscillation? Okay. No oscillation means either critically damped or overdamped. So the blue and orange curves, there are no observed oscillations. That means that for no oscillations, R squared should either be greater than or equal to 4L over C. Okay. So from that condition that you need to satisfy, you can calculate for the resistance. The resistance should be greater than or equal to 180 ohms. Okay. So if you have more than 180 ohms of resistance, the dissipation in energy is so big that energy transfer does not occur between the inductor and the capacitor. Good. Any questions about LRC circuits, LR or LC circuits, or the concepts we've learned? Right. So this slide summarizes the key ideas. And with that, we end our lecture. And tomorrow will be the last discussion on AC circuits, where we now look at RLC in series with an alternating current source. So I wish you a good day, everyone, and see you in tomorrow's lecture.